Yeah, is the tech guy. Are you ready for recording?
Yeah.
Okay, so we can move on and introduce the speaker. Yeah, we want to, as part of the academic track section, we are in Chupa who will be presenting on the use of deep learning model for mapping dwellings in unplanned settlements, right?
Yes.
Okay.
I go ahead.
Yeah. Well, the recording tech, are you ready? Hello, who is there? Just wait.
Okay.
Yeah. Where's the recording? The tech person, are you here?
Yes, Victor, we're just waiting for you. Please go ahead.
Oh, okay. So, is the recording on? Is he ready to? So he's ready. So Blessing Chepa will be presenting on the use of deep learning models for mapping dwellings in unplanned settlements. And that's part of the academic track section. So over to you, Blessings.
Thank you very much, Victor. When you hear the word AI, artificial intelligence, what comes to your mind? Are you excited or threatened? My name is Blessings Cheva, and I'll be presenting on the use of deep learning models, which is part of artificial intelligence for mapping dwellings in unplanned settlements. And I am a PhD student at the Liverpool School of Tropical Medicine. And I also work at the Malawi River Outcome Trust under the Vector Biology Research Group. So just to give you a bit of an introduction, we understand that mapping individual dwellings is important for urban planning, for emergency preparedness, as well as for offering of grid services like electricity and water. But the process of creating these individual buildings is slow, time-consuming, and also intensive. Recently, the use of artificial intelligence combined with remote sensing has attempted to automate this process of mapping dwellings. And there have been studies before that have used deep learning models to map dwellings. However, such studies have been conducted in areas where, like rural areas, where buildings are apparent, where you can actually see that this is a building, and also in developed countries where they have a well-planned area, and it's easy to detect those elements from a satellite imagery. So there exists a gap in literature to see how we can train models that actually can work to detect buildings in unplanned settlements and also in low-income countries. As of now, the hypothesis is that the current deep learning models do not benefit low-income countries and unplanned settlements. So it's not clear whether how we can train or fine-tune a model that is going to be specific for unplanned settlements. For example, cases of most countries, most settlements in Africa. So the aim of this study was to automatically map building footprints from high-resolution satellites and aerial images using artificial intelligence in unplanned urban settlements. And specifically, I wanted to train and fine-tune an existing model that could be able to extract buildings from a remote sensing imagery, and then to evaluate that model in terms of performance, and then at last to make recommendations based on the findings. So what did I do? The first part, I obtained a global data set called SpaceNet. This one has got over 30,000 buildings, labeled buildings of Khartoum, Vegas, Paris, and Shanghai. And then I used a mask regional-based convolutional neural network. So this is a model that is a deep learning model. I trained my model using this SpaceNet dataset. SpaceNet dataset is available online and it's for free. And then afterwards, I tried to see the results by doing model inference. And the second part, after that, I then went on to my study area, which had 3 unplanned settlements, one in Nairobi, Kenya, another one in Lima, Peru, and the last one was in Cap-Haïtien in Haiti. And I also made a customized data set from these settlements, meaning the buildings. I digitized the buildings and put the labels there, and it trained also using the mask RCNN, and then also did the model inference. And the last part, I started to customize this model that I've created in terms of fine-tuning what we call hyperparameters to see how it's going to perform after those has been optimized. So in essence, that's the methodology that you are seeing here. And just to mention that in the first model, I used what we call common objects in context weights as part of my modeling. So this is basically a data set of, it's also open, you can download it. It's a data set of objects that have been already labeled that help to improve the performance of your model. So as I said, I had a 3 steps methodology. So in the first step, what you are seeing is an result from an original image as how the image is looking at satellite imagery and when you have the labels. The second picture on the middle is an inferred image using a mask RCNN model that has been trained on a SpaceNet. And the last one to the right is an inferred image that has been used by a customized model and that has been trained on a customized data set. So what you can see from these results is that if you look at the picture in the middle, that's the inferred image from mask RCNN trained on SpaceNet. Those that are what you see as colorful patches or colorful polygons in green, yellow, or orange, and all that, those are buildings that the model was able to detect using the mask RCNN trained on SpaceNet. And you can see the shapes are a bit funny as well. Those are the delineation of the polygon. And what's on the right is the same, but as you can see that they have improved in terms of both the detection and also the delineation of the polygons. So in the model trained on SpaceNet, you can see that maybe there are 20 or 25 buildings that have been detected. Apart from the detection, you can see also that the boundaries are quite incorrect in terms of the boundaries of the buildings. Whilst on the right, when it has been trained on a customized data set and has been optimized, you can see that quite the number of buildings there that have been detected. And also the bounding boxes are quite accurate. And you can see that it missed some which are like, some are like fences, and that's pretty good because it's able to detect that this is a fence and this is an actual building. So when I did the model inference, I also tried to look at the matrix, the confusion matrix, which actually measures the errors or the performance of the model. So I looked at the intersection over union, which is basically the overlap, the ratio of overlap between what your model has predicted and what is actually there. So when you look at the building and the building footprint that has been predicted by the model, that's the intersection over union. And then there's the precision, which is what the real features on the ground have, how much have been correctly classified on the map. So that's the precision. And the recall measures a class on the map, how often a class on the map is present on the ground. And the F1 score is like a harmonic mean between the precision and the recall. And then there's the overall accuracy. So basically what you're seeing, you should look at the numbers in board. Those numbers are supposed in a distribution to be 1. So 1 is the best and 0 is the least. So if you look at the SpaceNet trend, we are looking at focus on the buildings, compare it with the custom trend and fine-tuned, also focus is on the building. You see that there was a big improvement in almost all the aspects of the models. I'll talk especially on the F1 score because it's like a mean between precision and recall, so that's a good measure actually. On the SpaceNet, it was 0.46, and on the trend, it was 0.66. And if you look at the overall accuracy, it was 0.65, and on the customized model, it was on 0.88, which is a big improvement. What can we make of these results? The mascara sending trend on SpaceNet data, and in fact on the same data, achieved a high performance. So when I trained the model based on SpaceNet and just split the same SpaceNet data in terms of model trained data set and inferred data set, it performed very good with a F1 scale of 0.78. And this result is even better than what other studies have found before. But when I took the same model and inferred it on my field study sites that are unplanned and mostly in low-income countries, the same model performed poorly with a 0.46 F1 score and an accuracy of 0.65. So you can see the two pictures there. Picture A to your left is from Vegas, from the SpaceNet dataset, how the buildings look like. And the picture on the right is from Lima, Peru, in one of the unplanned settlements, and that's how buildings look like. So basically, this explains why the model was able to detect its own buildings trained on SpaceNet dataset and unable to detect buildings that are in unplanned settlements. You can imagine the color of the roof, the shape of the buildings, the demarcation of roads are all completely different, and that's why basically the model was unable to differentiate these two. However, when I retrained the same model with customized data set from these study sites, it improved the performance by 37% in terms of F1 score and 35% in terms of overall accuracy. And both the previous slide and this one just conclude that the hypothesis was right, that models that have been trained and developed for that are available are not accurate, do not perform when they are presented with data from unplanned settlements and low-income countries. When I tried to change the parameters of the model, there was a slight increment in terms of performance, but I noticed that there was a trade-off in a sense that you either lose recall or precision when you are fine-tuning the parameters. So you may change some parameters in the model, but there's a trade-off between recall and precision that must be accounted for. So what I concluded from this is that if you want to perform a mapping session using deep learning models, then alone a deep learning model cannot map like 100%. You can see even with the fine-tuning, I only achieved 88% accuracy, meaning that there was 18% that was missed in the detection. So if you take that approach alone on its own, the AI approach, you will not be able to actually realize 100% accuracy of the model performance. But at the same time, if you just map the buildings manually, as we do now using Mapathon and all that, you see that it's time consuming. It's sometimes can be expensive as well. And that's also not ideal. So the best recommendation that I can make from this study is that it's better to use a hybrid approach where you map using AI first, and afterwards you submit that data to OSM, for example, and people continue to digitize. And that way we'll be able to map these urban settlements that are unplanned accurately. And also it's recommended to use high resolution images for customized data set. and employ a robust manual digitization approach. So these models actually, it's garbage in, garbage out. So the data that you feed it is as important as the results that you're expecting from the model itself. So you can see that if you have a high resolution image, it will improve your model performance. If you employ a more robust manual digitization approach, you also improve the performance of the model. However, as I only trained on three cities and limited data, I recommend if those would want to do some further studies, can look at how model dynamics change if you have more data to train it on, and also to experiment further on the parameters that you can fine tune on the model, just to see the impact of that. And I would like also to see, I know there are some ongoing studies that are using, for example, OSM data to train these models, and how that would perform in unplanned settlements in low-income countries. So basically, that's a study that I wanted to present, and I must agree that it's quite exciting for me and also challenging to present this AI study at a time when it's being questioned a lot in the media platforms. You have heard a lot about AI and the use of AI. Is it good? Is it bad? So yeah, I expect some questions and discussion from this discussion. And thank you very much. If you have questions and you want us to discuss something about this study, the floor is open. Thank you very much. Over to you, Victor.
Yeah, thank you, Blessing, Chepa, for your amazing presentation. Let's have questions from the audience.
Hi, Blessings. We have a question here.
Okay, I followed your presentation, and you said that when you get those data, it's possible for you guys to upload it in OSM. You know, we have challenges maybe sometimes with AI. So what validation method do you guys use to make sure that data uploaded there are very accurate and validated? Thank you.
Thank you for that question. Indeed, there's need to validate and to check whether this data is accurate. From the modeling aspect, you looking at the confusion matrix can actually tell you about the performance of the model. As I showed you, I'll just go back to that slide with the results. So you have something like this for the whole area. And what I was explaining in terms of the confusion matrix, actually, that's a good indicator of the performance of the data. But now, indeed, that's a good question of this. How can someone now validate it on the OSM? And I remember when I met, I think, Geoffrey in Uganda, I asked him the same question in terms of if someone has a data set that has been generated like this one, how do we validate it? So I think on the side of modeling, we validate it by using the confusion matrix, the performance of the model itself. But on the side of OpenStreet mapping, maybe Geoffrey or someone from OSM should be able to answer that. So I'll return that question back to the audience or someone who is very familiar with the validation process in terms of OSM workflow. Anyone? Geoffrey, you want to come in on that?
Yeah.
Sorry to put you on the spot.
Any more questions?
Yeah, I'll just come in quickly. So yeah, I think the process we use for OpenStreetMap, of course, we use AI generated data, but then it has to be verified by a human before it is imported into OSM. So we don't just get, like a lot of data and then just do one bulk upload. Still, it goes through the process of, a person like checks the AI data and then pushes it to OSM. That's, I think, kind of the validation process here. So however much AI, is useful for OpenStreetMap, but still, we need to retain the human part of OpenStreetMap because it's equally important. Hope that helps. But yeah, there's another question here from Severin, so I'll hand over to him.
Hello. Thank you for your presentation. I had a question about actually
all that you developed, the training, the methodology, and also the hyperparameters, is it everything open source, or it's a black box? Just to know if AI can or will be open to everyone, so that we know when we use these technologies, how they work basically, and or if it's out of the blue and we cannot actually have the whole overview of what they're doing, except the result there, the product.
Okay. Thank you for that question as well. Very interesting question. So in my methodology, what I've used here, they are open and available. The mask CNN model is an open source. It's available on the GitHub and other platforms that you can access. So it's available. And the first data set from the SpaceNet is also available, free and open source. Cocoa Weights, the common objects in context, is also available. It's from Microsoft. So all that is available. What is not available in this methodology is the customized data set and the hyperparameter tuning that I did. So this was part of my master's research. And as we are talking, we are in the preparation of a manuscript. So once that is published, this will be available as well. And the data sets will be uploaded on an open source platform where you can download and experiment for your own further studies. So be on the lookout. You can contact me. We can connect on LinkedIn, and soon maybe that publication will come up and you see the rest of the data sets that are not available open as of now. Thank you.
Yeah, thank you. Blessings, Chepa, for responding to the questions. In the absence of any other question, I want to appreciate everyone for joining this section. I think after the break, we'll be having the last section of the academic track. Thank you, everyone.
Thank you very much.
Thank you.
Thank you.